All right, let's take a look at transistor biasing. We're going to look at the simplest form of biasing, the BJT base bias. So in order to analyze this circuit, we're going to write a Kirchhoff voltage loop equation. And to maybe clarify that just a little bit, let's go ahead and put in how our VCC is going to be hooked up. So this is our VCC supply voltage hooked up to the circuit. This just makes it easy to see your loop equation. I'm also going to put in my polarities here for my resistor, RB, and my VBE. So there's my polarities. Now here is my loop equation. If I start right here, I get minus VCC plus VRB plus VBE, and I'm back to where I started, so Kirchhoff says all that should be equal to 0. Now we can see where we can solve for VRB. Just manipulate the equation so that we can solve for VRB. We can solve for IB now using Ohm's law. VRB divided by RB is IB. You can put it in terms of VCC minus VBE if you want to. Now that we have IB, we can pretty much solve everything else. We know that beta of the transistor is equal to IC over IB, so therefore we can multiply our IB that we just calculated by beta and get our IC. And once we've got IC, we can take that collector current, IC, times the RC, the resistor, the collector resistor, and find VRC. And now we can do another Kirchhoff loop equation here. And we've got VRC. So we can calculate from there our VCE point. So now we've got all of the voltage drops, individual voltage drops, and all the base current and the collector current figured out. The next thing to do is go ahead and build a DC load line and plot in the different points VCE cutoff, which basically in cutoff we're going to treat the transistor like it's a switch in the open position. Therefore VCE, if the switch is open, we would get all the voltage there. There would be no current flowing through RC at that time. So the voltage drop across RC would be 0, and if we do our Kirchhoff voltage loop equation, we would see VCE is equal to VCC in the cutoff state of that transistor. In saturation, we look at the opposite end of the spectrum, and we assume that the transistor is all the way short. And if the transistor is all the way short, we've got all of the voltage VCC being dropped across RC, and that gives us our saturation current. So here's our DC load line. You can see on our x-axis we've got VCE, voltage collector to emitter, on the transistor, and at the far right we've got our VCE cutoff point, which is equal to VCC of the circuit. And at that point our transistor is acting like an open switch. You can see there's 0 IC and maximum VCC. So the transistor is acting like an open switch. And on the opposite end of the DC load line, we've got our IC sat, which means we've got our maximum current through the collector at that point, but minimum 0 VCE voltage. And between those points, we can draw a straight line, and that is our active region there. And our Q point should be somewhere in that active region, preferably right in the middle or near the middle. And our Q point is our VCE IC of the circuit.